So, what do we mean by a statistical model, and what are the key features of statistical models? Well, we've come across this before in a sense already in what we've covered in the course. A statistical model is simply a mathematical model with a stochastic component of a process which generates the actual or potential data. So we talked about this in lecture 1. Stochastic because we're dealing with uncertainty. Now, so far we've considered statistical models for random variables with a PMF or a PDF that depends on parameters. So we've looked at models that fall in this class. Here we have the probability density for x given theta. This is the sample space. This is the parameter space. What we're going to do when the models we're looking at now is we're going to turn to models which seek to represent the relationship between two or more variables with unknown parameters. So we're talking about relational variation today. And a common objective is to model a dependent variable we're going to call y as a function of a vector of independent variables that we're going to denote x. And of course an error term because we are being stochastic about it, so there's a stochastic component to our models. And models of this type are known as regression models, and this process of modelling a dependent variable in relation to a set of independent variables is known as regression analysis. And the reason we want to build regression models, the reason we want to do this analysis, well, there's three main objectives. We might want to estimate parameters that describe how random variable y is related to random variable x. We might want to test hypotheses concerning specific aspects of the relationship between y and x, and we might want to predict values of y given changes in x. So just to give a concrete example, let's say we're interested in modelling road traffic accidents. First, estimate parameters. We might be interested in what effect do speed cameras have on road traffic accidents. So in that case, speed camera is x variable, road traffic accidents are the y variable. Test hypothesis. Once we've got a model, what range of road traffic accident outcomes are associated with a 10% increase in the number of speed cameras? So we're going to test some hypotheses about ranges in which the parameter value, ranges around the parameter value. Or prediction. What will happen to road traffic accidents if we introduce 100 new speed cameras on the road network? So that's an example of the sort of thing that a regression model can tell us about. Let's now turn to some definitions as usual. Okay, we've talked about this. We've got a dependent variable y. The dependent variable y, sometimes called the response or sometimes an outcome, and we're going to denote it capital Y because it's a random variable, is the random variable whose variation we would like to explain in terms of or conditional on other observable variables. So this is the point is we're trying to explain the variation of this variable in terms of the variation in a vector of other variables. And we're seeing y essentially as a function of x. And what we're saying is that the spread that we observe in y, its variance, can be explained by the spread that we observe in x and by an error term. So the independent variables, that's our x variables. We call them independent variables or explanatory variables, sometimes covariates. They're denoted x. They are the observed variables we're going to use to explain y, as I've just said. Thirdly, parameters. The model is going to contain a set of parameters or coefficients that we're going to denote by beta, and these are going to determine the relationship between y and x, so the direction of that relationship and its size. And these are unknown parameters, and that's the target of model estimation. We're going to try and estimate those parameters that tell us how x is related to y. And finally, we have our error term. The error term, sometimes called a disturbance, we're going to denote by this curly e, renders the relationship between y and x stochastic rather than deterministic. So generically, we can write our regression model in this form. Y is seen to be a function of x, an error term, and a set of parameters that determine the relationship between x and y. That's a very generic expression. But it's informative, though, to express regression models in conditional expectation form, because this allows us to distinguish a systematic component in the model from the random component. So in conditional expectation form, the regression model is written like this. The conditional expectation form of regression model is y is equal to the expectation of y given x. That is our model, the systematic part of the model, plus an error term. That's the random part of the model. So we're splitting the regression model into two parts. Systematic part that we're going to try and build a model for, and the random part that we're going to make some assumptions about the error term. Now, one of the assumptions we're going to make straight off is that the error term is distributed. The conditional expectation of the error term given the covariates is 0. And in the review slide here, that explains what this assumption means. It's an assumption that's typically made in regression. What it boils down to is, if we make this assumption on the error term itself has expectation 0, so it's random noise that is varying with around a mean of 0. And it also means that the error term is unrelated with x, so we can section things off in this way. X is separate in a sense from the error, because the error is uncorrelated with x. And if you review this slide here, that will show you why that is the case using the rules of covariance that we covered previously. So the conditional expectation form is useful because it emphasizes that the inference we're going to make about the relationship between y and x is conditional on our knowledge of x. Now, we don't observe this conditional expectation. Our model is going to try and approximate it in a sense. That's what the model is going to try to do. And we're going to do that by building a regression function. So the conditional expectation is modeled using a regression function. And the regression function notation is, we're going to use this letter mu, it's how it's normally written, x and beta. Notice the error term doesn't appear here as it did here, because we split the error term out. So we've got two parts to our model, the regression function and the error term. And the regression function depends on x, but it also depends on a parameter vector beta. And the regression function, its main property is going to tell us how the average value of y changes as elements of x change. Now, two other important points we're going to make today. Since this regression function depends on parameters beta, it is explicitly a parametric model because it depends on those parameters. Now, the form of this regression function could be linear or non-linear, and beta could take a variety of different forms. In this lecture, we're going to look at the simplest linear specification for the regression function. That is the linear regression model. So the structure of a regression model. A regression model consists of three things really. A functional form denoted by the function mu, a set of parameters denoted by beta, and that's beta naught up to beta k. So in this case, we have k parameters in the model, and a random error term or a disturbance term, curly e, with assumed properties, typically the one we've made earlier, that the conditional expectation of e given x equals the conditional expectation of e, which is equal to 0. So as I said, we're splitting the model into two parts. We're saying the model has two components. It's got a systematic component that's captured by the regression function, and a random component that's captured by the error term. The systematic component is capturing the systematic information that x can tell us, provide about y in the form of this conditional expectation. The random component of the model represents the fact that there's uncertainty, so it's representing the stochastic nature of the relationship we're looking at. And in regression, we're not dealing with deterministic relationships. We wouldn't need a regression if we had a deterministic relationship. We could just have a law or a rule that tells us precisely what's going to happen as x changes for y, in a way that, for instance, a mathematical equation does. We're not dealing in that realm. In the realm that we're in, there is uncertainty in the relationship between y and x, and that arises for a variety of reasons. It could arise just because of natural variation or randomness. So the relationship we're looking at does not follow a strictly predictable law. It could be that we don't observe everything that we want to observe. You know, our x vector is not as large as it might be, so there's unobserved explanatory variables. We can't model everything, and that introduces amount of uncertainty into the things that we can model. It may be we have measurement error in the model, so our measures of y and or x are imprecise in some sense and inexact, and that causes uncertainty. Or it could be this functional misspecification. So this functional form that we've chosen, mu, is not perfect in all cases. It's an approximation, and for that reason, again, there's uncertainty. So this term here, curly e, this is what it's capturing. It's capturing all of these random elements that cause uncertainty in the relationship between y and x. So, model development and form. How do we proceed in regression analysis? Well, we want to develop a model, and essentially this involves an iterative search for a specification, an ideal specification, or the best specification we can achieve. And that involves the choice of mu, beta, and the error term. Or not the error term, but assumptions about the error term. And we want to find a form that offers good explanatory power and is reasonably parsimonious. So explanatory power in the sense that as much of the variation of y is explained as possible by the model, and parsimonious in the sense that it's the least complex model we can obtain to perform this function of having good explanatory power. That's what parsimonious means. The least complex, the one involving, in a sense, the least variables or the least parameters. So the steps that we typically take in trying to develop a model are, first, we postulate a general class of models that's appropriate to the case in hand. And the linear regression model, for instance, may be one candidate that we choose in step one. We then identify a specific form for the model to be fitted. So we're going to identify our regression function. We then estimate the values of the parameters beta for this model that we've chosen. And we do this by applying an algorithm, a mathematical algorithm. And in this lecture, we're going to talk about two. We're going to talk about ordinary least squares and the maximum likelihood estimator. Having estimated the parameters, we're then going to perform diagnostic tests of goodness of fit and model validation. So in other words, we're going to conduct inference about the model itself, how well it's performed, and about the parameters in the model. If the model fails in the sense that this step 4 says we're not doing a very good job, then it's back to step 2. If this looks as if we are doing quite a good job, then we might accept this model, but of course we can build on it in further analysis if necessary. Okay, so as I said, the regression function could be linear or non-linear in beta. In this lecture, we're going to restrict ourselves to linear models. These are models that take this form here in matrix notation, and we're going to go on and look in detail at this form in the next part of the lecture.